Hey, chemistry! Welcome back to Mole Island. Today, we are just going to be on Mole Island. So sit back and relax and enjoy your stay. It's an easy stay today. Mole ratios. Okay, mole ratios you have to think of kind of like a recipe. If I am going to make one cake, and for every cake, I'm going to need 3 eggs. If I wanted to make 5 cakes, you could probably tell me easily how many eggs I'm going to need. But since this is chemistry, let's just set it up. I want 5 cakes. And I want to know how many eggs I'm going to need in those 5 cakes. Well, for every 1 cake I make, I need 3 eggs. And what I've done here is I've multiplied what I want by my ratio. This is a 1 cake to 3 egg ratio. So 5 times 3 is 15, so obviously I'm going to need 15 eggs. Mole ratio is no more difficult than this. It's setting it up right so that you can get the proper mole that you need. Let's just look at our first problem. I have hydrogen gas plus oxygen, and those react to form water. Here I have a synthesis reaction, and I've balanced it for you. What this says is that there are 2 moles of hydrogen gas and 1 mole of oxygen gas on that side of the reaction, and those react to form and make 2 moles of water. These are technically ratios. The coefficients in front of the compounds are ratios. So I could say that there are, for every 2 moles of hydrogen gas, I'm going to need 1 mole of oxygen gas. For every 2 moles of water, I'm going to need 2 moles of hydrogen gas. And so you have to think of the coefficients as ratios. Here I have on this side, in this problem number 2, I have a little more complicated reaction, but it's still balanced for you. This single replacement reaction takes potassium and uses 6 moles of it and 1 mole of diboron trioxide to, in a single replacement reaction, make 3 moles of potassium oxide and 2 moles of a boron atom. Here we could say that for every 6 moles of potassium, there are 1 moles of diboron trioxide. But what if I had 4.5 moles of potassium? Then how much of that would I need? So we would need to set that up. We would say I have 4.5, because your given always goes first, moles of potassium. How many moles of, we'll just say, diboron trioxide are we going to need? Well, for every 6 moles of potassium, there's 1 mole of B2O3. Okay, so my moles of potassium will cross out, and I get 4.5 divided by 6, which gives me 0.75, and that's going to be moles of B2O3. That's a 3. I'm having a hard time writing. Okay, so we can practice this before we move on to stoichiometry, because really you can set this up. You're basically creating your own unit conversion, mole to mole, by using the coefficients to travel across the reaction. We know how many moles of this we can make based on how many moles of one or two things that are given to us. So on your mole ratio, I'm going to ask you to use the following balanced equations to write the mole ratios. I'm going to do the first one for you because, number one right here, I want you to see how many possibilities there are and basically what to do. Okay, I can have 2 moles of H2 for every 1 mole of O2. For every 2 moles of H2, I will also make 2 moles of water. For every 2 moles of water, I will make 1 mole of O2. For every 2 moles of water, I will make 2 moles of H2. For every 1 mole of oxygen, I will make 2 moles of H2. And for every 1 mole of oxygen, I will make 2 moles of water. So as you can see, out of that little tiny reaction, there's a lot of mole ratios. Essentially what this means is that there are really 2 mole islands, okay? And there's a mole island for compound A, and there's a mole island for compound B. And you can travel back and forth to those islands by using a mole ratio. All right, chemistry. I bet you know what comes next. You are going to go to my big archipelago.